Alright, hey class. I don't love either of the videos that we found for this lesson, so I'm going to try to record another one, but my kids are on the loose, and they're probably going to scream again. So I don't know if you liked that thing from the last video where they were screaming. Maybe you'll like this too. Anyway, I'm going to go. Here we go. The big thing for this lesson is to try to tackle this ambiguous case stuff, that for some sets of given information, there might be no triangle possible at all. There might be exactly one triangle defined uniquely, or there might even be two, and it's not listed here, but there could even sometimes be infinitely many possible triangles. So let's see. So I would break this down by those old rules from geometry that you used to use to prove that triangles were congruent. And that should give you some hint that if side, side, side proved that two triangles were congruent to each other, the reason they did that is because there was only one triangle possible. So if you had a triangle and then a ostensibly different triangle, it couldn't actually be different if they had the same sides. Okay, here's what I mean. Let me see if this makes any kind of sense. This thing. So basically, look in here. This would represent three sides, right? And I'll stick these two sides together so they share this endpoint. And then what I could do is I could orient this, and I'm changing the angle. They didn't tell me a specific angle, so the angle would be allowed to vary. But I can't change the lengths. I can't take this thing and stretch it or shrink it. It's got to be whatever it was. But I'm going to take this now. I'm going to stick it at the other end. And I now have those two endpoints stuck together. And what you'll see is the only way to actually enclose a triangle is to find oh, did I nail it on the first try? Look at me. But I'd have to find the position where these guys just perfectly fit together. Let's pretend for a second that I didn't nail it on the first try. What I mean is maybe we try to make these things reach. And I take this side and I try to shrink it down. But no, it doesn't quite reach. You can see I'd have to open this up again, right? And so the only position where I can make these things fit together is that one position. And no matter how I tried to fit these together differently, I would always get this exact triangle again. So that means if you were solving this triangle, then angle A would be something, angle B would be something else, angle C would be something else, and that's the only possible thing it could ever be. So side, side, side has one unique solution. Now I'm lying a little bit. There is a chance for side, side, side to actually give no solutions, but I want to talk about that later. It's not really the focus of today. Now we could do the same with side, angle, side. Okay, so for side, angle, side, I might kind of gray this angle out because the lengths here are not what's important, just the angle measure is. Now for side, angle, side, you'd have one of these sides running along this side of the angle. The other side would have to run along the other side of the angle. And in that way, maybe you can see that there's really no way to do this other than the way we just did. So I could take a blue marker. I could highlight that there's a triangle that starts down there, comes up here, goes down here, goes over there. So there. That triangle is one potential solution. Crud. Okay, so you might be thinking, yeah, but Mr. F, what if you took that one from the bottom and put it on the top instead? Maybe it can just run along the other side, up there. And maybe this side can run down here instead. And that's good thinking, I suppose. That might sound smart, but it ain't, because of course I can now connect these dots, make myself a red triangle. And at first glance, if you're not thinking, then you might think these triangles are different. But guess what? They're not. How do I move that guy out of my face? Alright, I could take these and I could, oh, I forgot about this thing. Alright, I could rotate this. And I think I have to reflect it too. It's hard to tell. I can't tell if this is just isosceles. But anyway, you can see those triangles are actually still the same, right? I haven't generated a new triangle just because it was kind of rotated around. That doesn't make it actually different, right? So there you go. That is sort of not really a proof, but kind of a proof, quote unquote, that side angle side yields the same results over and over again. But the real one we came to see is ASS or SSA. So I'm going to jump to that. This is the one where we might potentially get more than one correct answer. And so for this, every time I'm given an ASS situation, I always draw my angle sort of over here on the left and opening up to the right. And I always take the longer of the two sides and I place that along the angle. Not the horizontal part, but this part. And then what you do is you imagine this other side up here, and you imagine that side being allowed to swing like a pendulum, like this, swing, swing, swing. And so here, this is sort of the explanation for why you sometimes get more than one solution, is imagine if this side was given to be only this long. Well, look, I can put it here at the end of this thing, but as I swing it, it doesn't reach the other side at all. So this is a combination of stuff, an angle, a side, and a side, where this second side that you're given is so short that it doesn't reach the other side at all, so you get no solutions. Now there's also the option of what if this side is actually a little long. This is where you can get two solutions, because I could take this side and I could swing it in to here, and you now see that we formed a triangle. We get this triangle. Forgive me if I draw this sloppily. That wasn't bad. So we get that red boy, but I could take this side and without changing its length, I could let it swing over here. Now these angle measures change, but the angle measure that mattered over here didn't change. So this is a new triangle that technically has all the same measurements as the first one. And again, I can prove it to you. As I overlay the blue on the red, well look, they share this angle like they're supposed to. They share this side like they're supposed to. And then this side here is the same as this side here, because remember all I did with that one is swing it like a pendulum into two different positions. And so here's how you get your two different solutions, is that way. Now you might say, okay, what if this side was so long? What if it was so long that it was longer than the other given side? If it was longer than the other, then suddenly you can't swing it into two positions, because I can swing it way out to here and I get this big obtuse triangle. But if you try to swing it back to a second position, it's a no-go, because it misses the angle. It goes onto the wrong side of the vertex of that angle. And then there's one more secret option. What if this length of side was just the right length, maybe here, that it fits, but only if it's exactly perpendicular. So suddenly now if we try to swing it up, it doesn't reach, right? If we try to swing it in, it doesn't reach. It only fits just perfectly right at the 90-degree mark. And so that would give you one solution too. So I'm going to stop jabber-jawing and I'm going to actually do the actual problem here, and we'll do some actual measurements, so hang on a second. Okay, so here's the actual practice problem they gave you. I don't love it. I don't like that the triangle is already drawn. I wish that instead they just told you that you had the measure of an angle called A, and it was 30 degrees. And then I wish they told you you just had some side called B, and it was 10. And then this side here, if this is angle A, then that side 6 must be 6, must be A, sorry. But then it's sort of, it's your job to draw this. So forget all this. If you're given these three things, first of all, you would recognize that this is A, S, S, because you've got an angle and two sides. Now you might be thinking, how do I know when it's SAS? Well, it'll only be SAS when the angle's name is different from the side's name. What the hell do I mean by that? Well, A, B, C. If you had two sides and the angle that was between them, then you would have to have side A, side C, and angle B. So you see what I mean? You have SAS when the angle that you're given has a name that's different from the two sides. Notice that our angle shares its name with one of our sides. That means that one of our sides is opposite from our angle. So we have angle A, we also have side A, and then one of the other sides that we have is here. That's an ASS situation. So you can tell the difference based on the names of the parts. So anyway, once you know that what you're looking at is ASS, then you sketch this thing out. I draw myself a long horizontal line pointing to the right, and then I sketch my angle, which is 30 degrees. Now if that's angle A, then side A should be the one dangling down from the end. So that's the 6 one. So that means this one is B and it's 10. And so what I know then is my side A is going to hang down from here. So my job now then is, well, let's figure out exactly how long this is along a perpendicular line. And if side A is less than this measurement, then it will not fit at all. It'll swing back and forth and it won't make a triangle. Here's what I mean by that. Again, zoop. If my side is too short, then I can kind of stick it here. Let me get my little rotation tool again. And if I stick that here, then if this side is shorter than that pink height that I just drew, then we cannot get any triangle at all. Now what if this side is exactly equal to that pink? Then that's the situation where we just barely fit, creating one triangle. But if we try to swing into the two different positions, it doesn't work. It only fits just there. Now our third option is, what if we're just a wee bit longer? Then I can swing in to this position, making one triangle, or out to this position, making a second triangle. And that's called the ambiguous case, when there's two triangles. Lastly, there's one more cutoff, and that cutoff is side B itself. If we're longer than side B, if our length was like 12, then we can't swing in, we can only swing out. And so everything is based off of comparing the length of side A to the length of side B, and also to the length of this height, H. So let's find H. You will hopefully notice that H is actually the side of a right triangle. So we're back to being able to use SOHCAHTOA. So, looking at this from 30, H will always be opposite from 30. And the side that you choose that has a name different from A, meaning in this case the B, that'll always be the hypotenuse. And so we are always going to be using sine. We're going to take the sine of 30. We're going to set it equal to the opposite, which is our height. We're going to divide that by our hypotenuse, which is the side 10. And then we can see that our height is going to be 10 times the sine of 30. Now normally these trig values are irrational, ugly numbers, but sine of 30 you guys know is exactly 1/2. So that means we can actually evaluate this off the top of our heads. Half of 10 is just going to be 5. So we now have that value as a cutoff. And so we see that the 6 that we have, it is longer than H, but it's less than 10. So that's right in that sweet spot to give us two solutions. But all the follow-up problems we're going to ask you are going to ask you to find the value of B. Pretend you didn't know what B was, or pretend you didn't know what A was. We're going to ask you to give us the values of A that would produce no solution, or one solution, or two solutions. So let's do that. Since we have figured out that this little height is 5, we can see that one way, the only way to get no solution would be as if our A value was less than 5. Again, if we're less than 5, then we get that short little baby side that no matter how hard we try to stretch it, it just won't reach to the side and it won't close off any triangles at all. Now to get two solutions is probably the most important one, and to get two solutions was a range of values. We said A would have to be greater than 5. So 5 is the minimum possible, but A also has to be less than 10. Because the second we become 10 or more, then we can't form that second triangle. So the 2 solution thing is a window of values. We have to fall between the height and between the other given side. So how do I get, I think it looks like I screwed this up. I'm sorry. We said that a less than 5 was no solution. I wrote it in the wrong box. That's on me. That is my mistake. I apologize profusely. So how do you get exactly one solution? Well, there's actually 2 ways to get one solution. We said that if a was exactly 5, that'll do it. Because then you get the one unique right triangle. But it's also true that if a is greater than 10, actually greater than or equal to 10, you have to equal the 10, then when a is too long, then you can only swing into this one big long position. You can't swing it back. Remember that idea? But that's it. This is sort of today's lesson, is finding these ranges of values that generate the 1 solution, 2 solutions, no solutions for ASS triangles. Now ASS is the only one you have to care about this for. You can never get the ambiguous case for any orientation of stuff other than ASS. I don't know if I've been super clear, but let's do one more example and we'll find out. So here you go. This says determine if a triangle that has measure B at 82, side B at 17, and C at 15 has 1 or 2 or 0 possibilities. So first of all, is this even ASS? If you're not sure, just draw yourself a quick triangle. I see a B and a C. I'll assume the other thing is A, so ABC. They gave me angle B, that's 82. They gave me side B, that's 17. And they gave me side C, that's 15. So just a quick sketch shows you that yes, this is definitely ASS, as opposed to SAS, which is completely different, right? But no, this is definitely ASS. So I definitely have to worry about this. It might be 2 possible triangles. Now, I don't like to draw it like this. And once I know that I'm ASS, and once I know that I might have that ambiguous case, I always start by drawing myself a horizontal line that points to the right. And I draw my angle B here on the left-hand side. Now 82 is pretty damn close to 90, so that should be pretty daggone steep. I do try to draw these things pretty accurately. So that's an 82-degree angle. Now again, if this is angle B, then the other side called B is the one that'll be opposite from it. So that means C is 15. That means that I don't really have to do any math here, because 17 is longer than 15. That puts us into that window where this side, it's longer than 15. So the second I try to do that thing where I swing it into 2 positions, it's just not going to work. It's going to fail. Because it's too dang long. So if I grab this and try to swing it, I can show you that swinging it, wait, why? Oh, because I'm dumb. Sorry, put that there. And then we can swing this thing like a pendulum. And that side will happily swing out to here, creating 1 triangle. But the second you try to swing it back, it's not going to work. It doesn't hit the side. It's too long. So I actually don't need to do any math. I can say for this one that there is 1 solution. And I can say because side C, I guess really what I want to say is side B is greater than C. And so we're in that range. All right, that's not a good one. Let's do another one. There isn't another one. Awesome. So let's do number 9. Number 9 is the same as the example we just did, where I could draw a 32-degree angle if I wanted to. But again, it's the longer one. It's going to be this guy at 11, and 17 is the longer one. So again, we're in that situation where we'd only have 1 position. I think all of these are that way. That's why they're telling you to solve, because all of these have only 1 solution. Spoiler alert. God, we're at 20 minutes already. How do I do this? Let's try one of these. Okay, so for 13, you draw your 36-degree angle. You mark it A. That means this side out here will be 2, and the other side is 7. And I think you can probably guess That 2 is definitely going to be too short and we're going to have no solution. But again, this is definitely one where, I don't know, maybe it isn't. Let's solve for the height. We said that height is always going to be, well, the sine of 36 will equal that height divided by 7. So you'll do 7 times sine 36. Set that equal to h. So I just did that calculation. It is 4.114. So guess what? That means for number 13, we definitely have no solution because side A is less than our height. And that's your justification there. Again, I'm up at the 20-minute mark. I never wanted these videos to be that long, so I'm going to be quiet and we'll talk more in class tomorrow. Okay, bye.